Welcome back to the Algebra 2 Structure and Method textbook series. This is on Chapter 8, Section 6. It's just some useful theorems about polynomials. So today's lesson, we're going to learn how to solve a polynomial equation using a lot of different methods. Before we start, you should know how to divide using synthetic division, evaluate functions, and solve linear equations in one variable. You will also learn some lovely new words. Let's get started. For our warm-up, we're going to solve these five polynomials, not quadratics, using completing the square, factoring, or the quadratic formula. You may choose. Take your time, pause the video, do your thing, and come back. I'll show the answers in 3, 2, 1. Okay, how did this go? Because this is important. This material comes from a lot of different chapters, but today we're going to learn a method that combines all of them. So if you are not solid, go back and review. Let's get started. The following are equations that can be solved using factoring, completing the square, the quadratic formula, etc. The roots shown here are on the right. Now, each is a polynomial of the form p of x equals 0, and it has a degree of a polynomial equation listed here. Now notice that each of these equations, the number of roots is equal to the degree of the polynomial. This is true for any polynomial equation. Just keep in mind that the roots aren't always going to be real numbers. You'll have to include complex numbers as well. Now that we know the total number of roots for the polynomial, let's think about the nature of the roots. Let's begin with complex roots. These zeros always come in pairs, conjugate pairs. Therefore, if a polynomial equation has a plus bi as a root, then a minus bi must also be a root. So let's see how this theorem can help us solve polynomial equations. So for example 1, we're asked to find a cubic equation with integral coefficients that has 2 and 3 minus I as roots. Cubic equation, so 3 expected roots. The conjugate root theorem tells us right away that our third root has to be 3 plus I because we need the complex conjugate of 3 minus I. So I'm going to make a little room for my factors. I use big brackets for complex factors. You can use parentheses, it doesn't matter. And remember, each factor is x minus the root. Now, the hard part comes next. We have to simplify this. It takes a little bit of work, but we finally end up with x to the third minus 8x squared plus 22x minus 20. When you're in this simplification step, just take your time, try to be careful of errors, and be patient with yourself. For example 2, we need to solve a quadratic. Quartic? Remember, I always get this mixed up. X to the fourth minus 12x minus 5 equals 0, given that we have a complex root of negative 1 plus 2i. So like our previous example, we know right away that our conjugate root theorem tells us the other root must be negative 1 minus 2i. So next, I'm going to multiply these two factors. So negative 1 plus 2i and 1 minus 2i. Don't forget to subtract them from x. And I get x squared plus 2x plus 5. Now, this is a new factor of our fourth degree polynomial, so we can use long division to actually divide x to the fourth minus 12x minus 5 by x squared plus 2x plus 5. And I get my answer, which is x squared minus 2x minus 1. Okay, now we're going to take x squared minus 2x minus 1 and use the quadratic formula to solve that factor. And I get 1 plus or minus the square root of 2. So I need to gather everything together. Okay, so I know that I have negative 1 plus 2i, negative 1 minus 2i, 1 plus square root of 2, and 1 minus the square root of 2. Consolidate your solutions. So just to kind of break down what we did again, we start off with this fourth degree polynomial. We know one root. We know that because it's complex, we already know the second root. By multiplying those two roots together, we get a new factor. And that factor helped us break down our polynomial even further. So let's talk now about variation in signs. So consider a simplified polynomial p of x with terms arranged in decreasing degree of x. So x to the 6th minus 2x to the 4th minus 5x squared plus 3x minus 6. I'd like you to take a moment and try and find how many sign changes we have in this polynomial. Pause the video and restart when you're ready. I will start in 3, 2, 1. Okay. 1, 2, 3 changes in sign. Hopefully you got the same thing. We need this for Descartes' rule of signs. So I'm going to state it formally, and then we'll talk through it a little bit more casually to make sure that you completely understand. Suppose we have a polynomial p. The Descartes rule of sign tells us of the number of positive real zeros and the number of negative real zeros. The number of positive real zeros is equal to the number of sign changes of p of x, or less than that by an even integer. So if you have 4 sign changes, you can have 4, 2, or 0 positive real zeros. On the other side, to find our negative real zeros, we take p of negative x and find the sign changes, and that varies by an even integer as well. So if you have 7, it could be 7 sign changes. It could be 7, 5, 3, etc. All right, let's see if we can see this in action. So example 3 says we need to list the possibilities for the nature of the roots, positive, real, negative real, and imaginary for the equation p of x equals 0. Now keep in mind that we have the total number of roots, because we know what the degree is, and then we have Descartes' rule of signs that can tell us the positive and negative roots. Take a minute and try this one on your own, and I'm going to start now. So for p of x, we have 2 changes in sign. So there are either 2 or 0 positive real zeros. Now we need to calculate p of negative x. All we do is plug in negative x for each value of x and simplify. We get negative x to the 5th, blah, 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 blah. Long polynomial. But we need to look at the sign changes for this as well. I see 1, 2. That actually should be scooched over a little bit. I see 3 changes in sign. So that means I have 3 or 1 negative real zeros. Now let's take all this information and go to the next slide to analyze it. So now we need to think about the possibilities. So based on our work with p of x, we have either 2 or 0 positive real zeros, and p of negative x told us 3 or 1 negative real zeros. So we're going to add those possibilities to the table. So it can be 2 and 3, 2 and 1, or 0 and 3, and 0 and 1. Now, for our imaginary roots, we're going to take the fact that we have 5 total roots, and we're going to subtract the sum of our positive and negative real numbers. So for our first entry, we have no imaginary roots because 2 plus 3 gives us all 5 roots. 2 plus 1 gives us 3 roots, so we have 2 imaginary roots left. 0 plus 3 gives us 3, we have 2 imaginary roots left, and then 0 plus 1 gives us 4. Same thing there, we have 0 plus 1 gives us 1, and then we have 4 imaginary roots left. And we have our answer. Great job today. This is a dense lesson with a lot of information, so please take your time. Feel free to review it, etc. Do extra practice with your teacher, whatever you need to do. But it's time to show what you know. Turn to your partner and tell them what Descartes' rule of signs is and what information it provides. I will see you in the next video.